I'm going to talk about the PhD thesis, which is towards sustainable transportation, a framework for AI optimization. So this is the work done under supervision of Mochen and Edward Park. So here's the outline. We will start from some background. We do some research objectives. Then we talk about a unified framework, which we're going to use throughout the thesis and for different projects. Then we'll talk about the algorithms and results. More specifically, we have 4 different projects. The first one, we will talk about traffic light control with the eco light. So it's a weighted reward with RL. I've been published in Nuance Workshop and IRAS. And then we talk about autonomous driving with LetFuser and MFuser. It's a transformer-based sensor fusion. I've been published in CPR Workshop and IRAS. And then we go over to vessel models, a predictive and sequential model, published in Ocean Engineering and AAAI student abstract. And finally, we talk about model-based ORL, which is an uncertainty-aware hybrid replay buffer with TD3 plus BC. Then we talk about the limitation and challenges, future direction, insights, and finally the conclusion. So about the background, first let's see about the environmental impact. So transportation accounts for about 28% of total US greenhouse gas emission, air pollution, and associated health risks. So we see the potential of the importance of environmental impact. Then we have complex decision making. Transportation systems specifically involve dynamic interactions and uncertainty that simple rule-based models cannot effectively manage. So we require some advanced machine learning model. And finally, generalizability. Developing an AI model for real-world system is challenging because there is a limited number of data, and we want to ensure that models generalize well across diverse dynamic environments. So more specifically, the goal is that we want to design and implement AI algorithms that improve operational efficiency and sustainability in real-world transportation. What's the scope? It's 3 different applications. We go from traffic signal control, autonomous driving, and maritime navigation. And throughout this project, we use different simulators like Sumo, Carla, Jim, and modular. If you look at here, on the y-axis, we have applicability, which goes from pure theoretical to simulations into real-world data, and finally, real-world interaction. And on the x-axis, we have the level of data abstraction. We have completely model-free, and then we have parameterized model, a state space model, latent space, and representation space. So we have different type of methods that can be kind of like spread out here. But what I want to pay attention to is basically where our each project is located. So DMFuser, which is for autonomous driving, is going to be something around here, which we use some latent space model during the simulation. The Ecolite is with a state space model with the simulation. And then we go for the Maritime model. It has some real world data with some parameterized and a space model. And finally, Moribrat, we are going to more latent space to get the result. So you can see none of them actually have a real world interaction. So now the questions that we want to answer in this thesis is that how we can develop some generalizable AI for unseen scenario in complex dynamic systems? Or how can AI optimize traffic flow and minimize emission in urban traffic systems? How sensor fusion in autonomous driving can be enhanced, and can predictive and sequential model enhance maritime navigation? So for that, we are going to propose a unified framework. It includes perception, which basically utilizes the real-time information from diverse sources and create a comprehensive representation. Then on the next stage, we have prediction or planning, which employ a sequential or predictive model to forecast future states and plan target trajectory. And finally, we have control optimization step, which leverage the rule-based or learning-based strategy to make decisions and execute actions. So here we have this ladder, including the perception, prediction, planning, and control. And we're going to see it a lot throughout the projects. First, traffic signal control. So what's the motivation? We have $124 billion per year on traffic congestion. 3 million deaths has been reported to air pollution, which 33% of it was for the traffic. And better traffic control in China has saved 15% of the delay. In the literature, we have non-learning based, which is using the fixed time control, actuated, web search, so SOTL. And then we have learning based, which use, for example, RL, such as DQ and DPG, or network, such as IntelliLite, to provide the solution. But what we're going to do is that we want to do it for the first time to reduce CO2 emission directly with different RL algorithms. And how we do that? We're going to prioritize inefficient vehicle using weighted reward. And finally, we're going to consider complex single intersection in Sumo with the TransCI, which is an API for Python. So Ecolite, what's the algorithm? Obviously, we're going to have our ladder in here. For the perception, we're going to use a state environment interaction, which is, in this case, going to be most recent green phase, the density, the queue length, and the type of vehicle. On the prediction stage, we are going to have our reward, which is basically on the literature, we have queue length, waiting time, and pressure. So you can see the equation of each of them in here. For queue length, this is for waiting time and pressure. And we are going to convert them to a weighted version, which basically means that not all of the road user will have same weights equal to 1. Some of them, for example, a bus will have a higher weight compared to, for example, a single car. And then we do it for the other basically rewards as well. And finally, the controller optimization, we're going to use our RL algorithm, which the action is the next green phase with the one-hot encoding. So here we can see the result. At first, we have 3 different metrics. We have travel time, CO2 emission, waiting time, and stop time. What we care about is mostly the CO2 emission, as we said, but also travel time is very important. And here we can see different ratios. The ratio are basically how many different cars are added. So 0% means all of the road user are basically the same. And then we have baseline and hours, which is basically the baseline is the original reward, and the hours is going to be the weighted one. For the baseline, we have the fixed time, which is basically is a non-learning base. And as we can see, as the ratio increase, the value of the corresponding measurements for the each of the measurements actually also increase, which makes it more difficult. If you look at the waiting time reward, we can actually see that for the CO2 emission that we care about, as we increase the number of this, the ratio, basically most of the time, our method is actually perform better compared to the other one. And the comparison are between DQN, A2C, and SARSA. And that's not the only thing. We can also take a look at the queue length, which is another reward. And we can see that for the CO2 emission, again, all of them for the 10% and 40%, they have been improved compared to the fixed time and also their counterpart, which is the baseline. And that's not just the case. It improved the CO2 emission, but also improved the travel time in some cases, for example, in A2C and travel time with DQN. And the same also goes for the pressure. So these are three different reward times, as we talked about in the previous slide. So now we want to say that, okay, we have developed something for the infrastructure, but can we actually move into some internal decision making? So what do we mean by that? Traffic signal control relies on aggregate traffic data and can use individual level adaptation. Individual adaptation means that the car itself or the vehicles itself. So traffic signal control can benefit from autonomous vehicles, which they can manage traffic flow, and it's also vice versa. Autonomous driving can also benefit from traffic signal control by enriching the perception, because as a part of the information, we can give them information about the traffic light, and it will help them. And here we can see the comparison between the two approaches, the waiting time SARSA and fixed time. Here we can see on the right side, the fixed time, the vehicles will actually need to stop along in here, which leads to more CO2 emission and also travel time. But it's not the case for waiting time. So given that, now let's move to the autonomous driving. So the motivation is that the sensor fusion in multimodal system requires integrated design, and learning separate tasks simultaneously will, with efficient methods, will enhance the performance, and computational limitation will hinder development of the complex model for real-world systems. So in the literature, we have decision-making for autonomous driving. We have imitation learning with behavior cloning, for example, or we have RL. Let's take a look at the imitation learning. Imitation learning itself relies on expert policy and data complementary, so completely limited to these two components. And then we have two types of this imitation learning. We have trajectory planning, which basically they generate a local waypoint, and then they have a separate controller like PID or MPC to follow it. Or we have end-to-end control, which is the rule-based that are trying to update the final vehicular command directly. So what our contribution? We have two methods. We have let fuser and the advanced version of it, which is DM fuser. For let fuser, we're going to augment the side cameras to enhance the perception and also develop a lightweight model for real-time sensor fusion. But in DM fuser, we will change the perception module with attention CNN and a GRE adjustment for the control module. And we're going to use a distillation for single task feature and modify gradient normalization for our multitask learning. And here you can see the results. Everything in yellow are the input. So we have the RGB as the input, and this is the depth information as input. And then we have some speed road command as input. And then here is the basically semantic segmentation. And this will create semantic segmentation, and we will basically create a top-down semantic depth cloud from it. And then we're going to use it. Every blue block is for perception, and the green is for control. And we create basically, we predict the speed traffic and also create a fusion module to predict the waypoint branch and the control branch. And then we have this yellow one, which are basically a single task, each of them predicting waypoint, throttle, steering, and brake separately. And then we have a student one, which has all of them at the same time. And we're going to use the adaptive feature matching to distill the knowledge from this into the final multitask network. So let's take a look at the let fuser. Bringing back the ladder, on the perception, we have RGBD. For the perception, we're going to encode sensor inputs to a representation space and create a top-down view semantic depth count, as we talked about. So here is a semantic depth count, which are different things inside the basically the scene is gonna be annotated separately. And then on the prediction planning, we have the decoding the feature to predict the value of interest, which in case is predicting the speed of the car, traffic light, a stop sign for the goal waypoint. And then finally, on the control optimization, we have a PID and also NLP for end-to-end control. So we're going to use PID on the fly and also end-to-end control for vehicle command. So as you can see, for the fuse feature, we have the measurement RGB feature and semantic depth cloud map. And then we're going to use batch normalization and concatenation. For the waypoints, we're going to use this fuse feature and create the static knowledge. And for dynamic, we use the static knowledge and also fuse feature to create the vehicular control. For training, we're going to use MGN and multi-agent control. As we mentioned, we have both PID and also imitation learning. But what about DM fuser? So DM fuser is going to basically change. The first thing is the fusion module. Instead of having a concatenation, we're going to have attention CNN. So attention CNN block you can see in here. We're just going to use the benefit of attention module for contextual information or global information, and also the CNN for the local information. And then the second is basically the dynamic head, which is going to change to dynamic branch. We're going to use a GRU loop. So we're going to have a separate GRU for the dynamic head to predict the vehicular command. And for our training, we're going to also use a distillation. So it's not just MGN for multitask learning. We're also going to use the distillation. So let's take a look at the result in here for the DM fuser. On the first one, we have some qualitative result. We have pedestrian crossing suddenly. So as a pedestrian is crossing suddenly, we can see that the PID control is telling us to brake, but the MLP control telling us to, for example, throttle. But we're going to follow the final control is going to follow basically the brake, which is the PID control. So in this scenario, we are going to follow the PID. But here, for example, on turning left, the brake, we have the brake, which is basically the PID control. However, the MLP control is going to throttle and also steer, which we are going to actually follow the MLP in this case because it is a maneuvering process. And finally, here is the last one, which is sudden red traffic light, which both of the PID and MLP are the same. So we're going to follow either of them. And now here is some quantitative result. Here we can see that for clear noon, we have the best result. And clear noon, a long path, which is a longer trip, we also have the best result. And for the all weather, sometime in normal situation and research situation, we either have the best or the second best result. And here we can see the evaluation study. So as we remove the components like the side semantic depth cloud, the vehicular command attention, and the distillation, we can see that almost always the results of one particular value of interest is going to decrease. So in overall, our method is basically the best. Can we actually transfer some knowledge from basically autonomous driving to navigation, since both of them are actually 2D navigation? So let's take a look at the similarity and difference. The similarity is that both of them have a dynamic agent interaction. So autonomous driving has with other road users and vessel has with other crafts. And the other one is that adherence to the constraints. So AD has the adherence to the traffic rules and vessel has with the scheduling. And then the difference is that the vessel models are more complex because of the complicated dynamic and the impact of the environment. And also the vessel full autonomy might be limited to since it has incomplete sensors. So now we're gonna propose a predictive and sequential model for maritime navigation. IMO, the motivation is that IMO target 15% emission cuts by 2030, and fuel consumption cuts with over 25% of vessel overall operational costs. So we have access to 2 years of Queen of Oak Bay, which is the road from Horseshoe Bay to Nanaimo. And here's the path for them. And when we look at the data, we saw that basically the difference is basically very large. Even though the path is the same, the fuel consumption is actually changing a lot. So we're going to take a closer look, and we saw that there is a correlation between the speed and basically the fuel efficiency. So if the captain actually tries to go very fast, we see that on the yellow region are the ones that are top worst, with the highest fuel consumption, and we saw that those are mostly inefficient because they are going very fast. So we take a look and see that what are the approaches in the literature. We have ship fuel consumption modeling are physics-based or log-based or sensor-based. And then we have different optimization methods, so rule-based, meta-heuristic, or order-based. So what we're going to do is that first, we want to have a predictive model so that use the domain-specific feature engineering. And then we're going to have sequential model, which is LSTM GRU architecture for road optimization. And we're going to create some artifacts, default and compatible dataset and reality-based simulation. And we're going to consider human in the loop architecture to inform captains about the decision by providing the insight and recommendation. So the algorithm, since we have the data, we need to do some pre-processing. So feature selection, domain knowledge, clustering the data, handling missing data, outlier detection, and then standardization or normalization. Bringing back the ladder on the perception, we have the domain knowledge. So we have the different states, which are some static states, such as trip start hour and direction. And then we have dynamic states like heading, rate, the water resistance, displacement, and the previous output. And then we also have the disturbances, so time, weekday, current, season, weather, wind, and water depth. We create and engineer the fuel efficiency, which is basically the fuel consumption divided by how much travel distance, and then the water resistance thrust divided by torque times speed. For the prediction planning, we have different actions, which is heading, shaft speed, and mode selection. And then for reward, we're going to consider some data and learning. We start from some frequent, and we consider going towards more sparse and goal-reaching rewards. For the artifact, we have the gym environment, which we created. It has like a conventional step render and reset. And then we have RL dataset, which has the observation, current, and next state. And then output, which is latitude, longitude, speed over graph, and ship fuel consumption. Here we can see the results of the predictive model. We can see that we have parametric, non-parametric, ensemble methods, and neural networks. The best of them for the R2 test is basically XGBoot. But when we look at the future prediction, which is basically with the horizon, we can see that it's not very good. So we look at the other methods. The other method also does not have a very good future estimation. So we said, okay, let's do another thing, which is basically sequential model. So for sequential model, we use a pre-trained informer model, and then we use a GRU as a residual prediction. And we have a sequence length of 25 minutes and then 5-minute prediction horizon. So here we can see the results for the different outputs, and we can see the non-autoregressive and autoregressive, and we can see that autoregressive actually provide the best result with the GRU, which is our approach. And here we can see compare the results. This is for fuel consumption, and here we can see that the basically the non-autoregressive might seem to be following it better, but basically the red one, which is the autoregressive, kind of also filtered the result as well. Now we want to talk about interactive to online. So can we address real-world constraints applicable across transportation domains, and can we do it only with real-world data? So the first thing that comes to my mind is imitation learning, like behavior cloning. But we saw that supervised method fails in adversarial situations, and also real-world usually lack large, high-quality data. So what's the next solution? So let's do reinforcement learning. But reinforcement learning has a generalization gap, which means that supervised method can learn from massive amounts of data, for example, internet, but RL in a closed world environment cannot do that. So for generalization, we need large capacity model and we need large trials. So it is impossible to do that in active learning, for example, in an on-policy or even off-policy. So what's the solution then? The solution is uncertain event model-based ORL. The motivation is that, let's say there are some situations that exploration is limited. Let's say the medical diagnosis or real world with safety constraint, or we have high generalizability is needed. For example, we want to go from simulation to reality, or we have adversarial situation and safety constraints. So how we can use some pre-collected demonstration from a starting point and then use them later on to fine-tune, or how we can learn the best possible policy from some offline trajectories. Here's one example. You see 3 different paths going, and we want to find what is the best optimal path from the first to the last. So the best optimal path turns out to be this one, which is basically the direct connection between them. But unfortunately, we cannot learn it from the data because we never see it inside the data. If you do behavior cloning, we are going to compute an average path. And obviously, this is not good. Can we do better than this? And it turns out, yes, with ORL, you can actually learn the red one, which is basically the best from the data. And how is that achieved? Is that it will learn the good stuff from the mix of good and bad. And here's the obvious one, like this one and this one will be completely ignored. And then we have generalization, which means good behavior in one place can suggest good behavior in others. For example, directly connected will result in not having this node as a connection and just go over it. And then stitching parts of good behaviors can be combined. So here, this good behavior is stitched to this good behavior. So that's the beauty of ORL, but ORL suffers from out of distribution. So the exploration will demand counterfactual, and it also wants to maximize it in the Bellman equation. So what's the common solution? We want to constrain the policy to remain close to the behavior policy. But this one is contradicting with the performing better than the average. We want to perform better than the data, right? So there's also another approach like reweighting the samples, but this one can induce artificial data who has the higher return. So for more feedback, we're going to have these 4 different steps. We have prioritized augmented replay buffer. So we're going to use on-policy simulator generated samples with repeated high or low quality samples in addition to the offline data. So this is idea coming from the Moore paper number 1. And then we have restrictive exploration. So we're going to have sensitivity and elbow loss, same as the Moore paper. And we also add a Monte Carlo deviation. And we create a measure of uncertainty loss, or UL. And then we're going to use that to truncate or penalize reward. So truncate basically our results if the UL is too large, and regularize our reward based on the UL. So regularize means that penalize our reward. And then finally, we use TD3 plus BC to train the model. So here is the roadmap. Starting from simulating, simulated training the VAE, and then going to restrictive exploration, data augmentation, policy update, and finally evaluating the model. Here we can see the result. We are comparing the random, medium, expert, and full replay of the 3 different tasks, half Cheetah, Hopper, and Walker, and also the average of them. We can see that Moriback actually performed better in the random and full replay. So these are the cases where we don't have high quality data. And here we can see the ablation. And for the ablation, we have shown that if we remove each of the components, then the result actually decreases almost all of it. So all of the components are necessary. Let's take a look at the results. So for traffic signal control, we actually reduced 26% CO2 reduction on average compared to static traffic for imbalanced traffic, regardless of what RL method we are using. And then, and even like the reward that we are choosing. And we also Not only the CO2 emission was reduced 26%, but also travel time was reduced as a byproduct by 7%. For autonomous driving, we have 115% driving score improvement on average compared to the baseline, regardless of the weather condition and scenario. And also, we improved 10% compared to the SOTA. For maritime navigation, 32% RMSE reduction achieved on average for the value of interest with the autoregressive VGRU, and 34% reduction compared to non-autoregressive. And finally, for ORL, with Moribrag, we achieved 19% performance gain achieving total reward on average for random and full replay dataset for various geometrical tasks compared to TD3 plus PC, and 5% increase compared to Rebrag, which is our baseline. But what are the limitations? There are still some limitations for each of them. So eco-like parameterized vehicles with inefficient fuel consumption, but this one shouldn't be considered as incentive. And real-time vehicle task detection requires intricate computer vision tasks. And we have the simulation to real gap. Then we have autonomous driving. The best results are limited to the experts because it was not RL, and synchronization is required between different sensors, and generalizability to unseen scenario is limited. For maritime navigation, rapid model update is required because the dynamic nature of the system, for example, aging, water resistance. And then we need to require real-time access to the features, and then the inference time is high. And then for Moribrag, we require reverse signal of offline metadata. It has complicated structure due to separate simulator package and optimizer step, and it exhibits conservatism when we have high-quality data set. So models will diverge over a long horizon and overfit to behavior false. So what's the future direction? For the traffic signal control, we can consider multiple intersection and network level coordination and collecting real-world data. For autonomous driving, we can use RL methods to learn decision making rather than mimicking the expert behavior and collect real-world data. For maritime navigation, we can consider periodic updating or gradual recommendation, tweaking based on the feedback from the captains, and then we can use ORL method to real-world data to optimize action and evaluating separate data. And for ORL itself, we can provide a mechanism for hyperparameter tuning, which will provide a mechanism to detect if we have high reward regions, so then we don't actually generate new samples that can increase the over conservatism. There are still some challenges, an open question of this case. So validation is a policy, validation in offline RL setting remains an open challenge question. The interpretability, even though it's very important, but in AI-driven solution is very critical to know what the AI model is doing under the hood, and it's still up to this day is unresolved. And data availability, which is basically the availability of high-quality data, is also limited, and it's not always available. So what the key takeaways that we get from this thesis? The first one is that weighted prioritization drives adaptive learning. So what do we mean by that? Inspired by multi-objective optimization, if you use weighted prioritization, effectively balance different criteria. So for example, we have that in our first project for weighted reward in traffic signal control that balance CO2 reduction and travel time. We have that for multitask learning for autonomous driving, and we also have that for prioritized replay buffer in Moribrag, which emphasizes on low or high reward regions. The second takeaway is that modular design enhances adaptability and performance. So inspired by a mixture of experts, the modular design improves flexibility in end-to-end design or distinct stage sharing. It doesn't matter if you do it end-to-end or distinct. The modular design actually improves the adaptability. And where we saw that, the first one is our unified framework, the ladder, to enable reliable solution for decision making. We also saw that in two-stage pipeline for Moribrag, and then we saw that in single path feature network of DM Fusion. The third takeaway is that model-based approaches enhance data efficiency. So by leveraging environmental continuity and smoothness, model-based methods improve generalizability. We saw that in Moribrag, we generate realistic transitions, which enrich our buffer and reduce the over-reliance on the dataset. So our on-policy exploration eventually lead to greater generalization capability. And finally, curriculum learning will help in difficult tasks. So simpler tasks will simplify learning of more intricate ones. For example, in maritime navigation, we start with some functional model, paving the way for sequential model, and handle progressively larger prediction horizon in autoregressive manner. Hope to move towards more sustainable and efficient and safer environments. And thanks for listening. If you have any question, I'm happy to answer.